Thank you. Thank you, Ben, for your kind invitation. And thank you all for being connected. My talk will concern recent work in collaboration with Philippe Chartier and Michel Koskas, Philippe Chartier from INRIA and Michel Koskas from Ravel Technology. So before getting to the heart of the subject, of the topic, allow me just to say maybe a few general facts about homomorphic encryptions, even if I know that you are already very familiar with the concept. So I just maybe say a few words. Okay. In fact, what is the definition of the homomorphic property? So data encryption system is said to be homomorphic, as you know, if it allows computations to be performed directly on encrypted data without decrypting it, while ensuring that the decrypted result is correct. This is the definition, simple definition of homomorphic encryption. So I will not take too much time to describe the applications, because I don't need to convince you that homomorphic encryption has many, at least potential applications and very famous applications. But I just wanted to say that the homomorphic encryption is in fact a theoretical concept which is known since 1978, almost. And most of the homomorphic encryption are now based on the so-called learning with error problem, which was introduced by Regev in 2005. And it is believed to be quantum resistant. So it's very interesting from this point of view, from this aspect point of view. So in fact, the problem is, as you know, the LWE based encryption are much involve some noise because they need to be secure. The noise is essential for the security. And the problem is that this noise grows along with the operation on the ciphertext and can make the decryption completely incorrect at some point. So it is the challenge in general is to try to refresh or try to remove the error, or to reduce at least the error of this noise, but without decrypting the data. And this is was really a challenge. And this has been made possible since 2009 by the seminal work of Gentry, who introduced a notion of bootstrapping. So bootstrapping is a sort of blind decryption. This bootstrapping techniques allows us to decrypt to decrypt in some sense, to decrypt the ciphertext, but with an encrypted key in some sense. This is why we can call it blind decryption, which is equivalent to bootstrapping. So these are things that you know very well. So let me go to the problem. So our goal, let me just describe maybe the goal of this contribution. The main goal, just described in a few words. So what is the goal of this contribution? This contribution concerns the ring LWE encryptions. And the ring LWE encryptions are based on the usual polynomial space, which are the field K here, which is the space of polynomials modulo phi m, polynomials with the rational coefficients. So this is a field, and this is also a linear space on Q. This R is it's a ring. It's a ring of integer of this field, and RQ is the finite version of this ring. It's based on ZQ instead of to be based on Z. And this phi m is the cyclotomic polynomial, in fact, of index M. So, So in fact, most, if not all, most ring LWE-based FHE system use a power of 2 integer. N is equal to power sum alpha. And in this case, the cyclotomic polynomial is very simple. It's just x to the power n plus 1, where n is equal m over 2. I should say there is a notable exception, which is the work by Joie and Walter, where the case n equal to 2 power alpha times 3 power beta has been investigated. So our aim is to extend these, extend in a simple way the main functionalities in FHEW, to be precise, or TFHE based system. And we want to extend this functionality to general M, which I mean by general M, an integer M, which is product of prime powers for some primes T1, T2 until TR. And we will be concerned just for the first, we're concerned with the first step, which is M equal 1 power, well, prime power, which is M is equal, it is 1 prime power, where T is a prime, okay? So what I mean by main functionalities, well, what we will do is to give a new formulations of the main functionality, like, for example, efficient modulo, which is the most simple one, and it's not new. It's just we should start by this, and we also want to give formulations of algebraic formulation of generalized extraction, sort of generalized extraction, or a blind, what we call blind extraction. We will explain all this in details. We would like also, and that's what we did, to reformulate the bootstrap in this context, give a new formulation of the bootstrap, and also to give a way to perform fast packing. You know that packing is in general very expensive. It's like a bootstrap in some sense, or roughly speaking, if you want to pack mini ciphertext. Okay, and to do this, we need and we shall use some mathematical tools, namely traces, duality, and scalar product. We will define all these objects in a way that makes all the construction systematic and more structured. At least we hope to. And even we can see some simplification, even that we can apply even for the power 2 case. So you should ask me maybe why we want to deal with general cyclotomic polynomials than power 2. We want to generalize this cyclotomic polynomial sets spaces. But in fact, the most maybe trivial argument is the flexibility of the parameter M, and it is clear that the values described by T power alpha are the values, the spectrum of the values is much larger, because you have 2 parameters instead of to have only 1 in the case of power 2 parameters M. So in this table, you can see that the power 2 values in red, and all the other powers all the other powers in black, and this is the value. These are the values between 500 and 10,000, for example. And we see that you have flexibility in the choice of this parameter. Okay. Now, there are many other advantages to use more general cyclotomic polynomials. For example, we know, as I think you know also, that in the bootstrapping process, especially when you are working with FHEW or TFHE, you have the so-called nega cyclicity condition. You cannot bootstrap to any function of the message. Your function should satisfy some condition which penalize, in some sense, the process of bootstrapping. And when you allow more general cyclotomic polynomials, then this condition will disappear, and we'll show you how it disappear completely. And this is a real advantage, because in fact this penalization may be even worse when using, for example, the Chinese remainder or the RNS, which is the same, Chinese remainder theorem representation for large messages. You can also have, by the use of general cyclotomic polynomial, you can also have more flexibility in the entity-like algorithm. So in some cases, as you know, probably know, you cannot use FFT because of the interaction with the modulo Q in general, because FFT may fail in some cases. Then you need, in some cases, you need to use the so-called entity-like algorithms. And the use of entity-like algorithms needs some special choice of the parameters Q and M. So the flexibility is guaranteed by this by general cyclotomic polynomials. There is maybe the last advantage, but not the least, is the case of we want, in fact, to extend all this encryption to general composite M, because in fact we discovered that there is a paper by Lubashevsky, Peckert, and Regev, in which they develop a certain number of techniques using tensorization techniques to accelerate the computations. When you have heavy computations on, say, ciphertext, the tensorization, they develop some tensorization linked to this form of M that may help very much, at least we hope. Okay. So now in fact, our study will, our analysis, our construction will be built starting from two main papers. The first paper is by Duca and Misiencio, which is maybe the encryption system. And in this work, Duca and Misiencio, they introduce a new formulation of the bootstrap, which allows a significant gain in the complexity. In the complexity of the bootstrap. As you know, the bootstrap is in general very expensive. And then comes the other work, which is based on TFHE. It's a version, it's another system of another encryption system, but it's very similar, where they use really the same bootstrapping techniques, but where they perform the evaluation of the bootstrap in a certain way that makes allows them to have a significant gain, further significant gain in bootstrapping. So let me just, we prefer maybe here to choose the framework of the Torus instead of ZQ, but it's the same. It's really the same case. It's just for maybe for convenience to choose the Torus instead of ZQ or Z or ZQ. Okay, so the Torus, as you know, is just the real numbers quotiented by Z. And the discrete torus TP is just 1 over P multiplied by ZP. So the TP is, we can define addition and multiplication on TP like if you define it on ZP, it's the same. So there is nothing to say here, nothing more. Oh. We can encrypt, we can define, this is the usual encryption, it's the LWU encryption, or TLWU, but we prefer to call it LWE encryptions. We take a message mu in the torus, okay, S in Z to N, vector S, and we, as usual, you sample A uniformly in T to N. You sample noise with the Gaussian, with the normalized Gaussian with standard deviation sigma, and you compute B as being the scalar product of A by S plus mu plus E, and you obtain your encryption as being the vector E and the quantity B, okay? And the decryption will be correct. Decryption consists in computing the phase B minus SA and project it on to the closest element of TP. The encryption is correct if the error that we introduce in the encryption is smaller than 1 over 2p. Okay, and the ring LWE is the same, it's based on the same process, and I don't present it because you know this very well. And you see that here you have of course a constant on the error in order to have a correct decryption. So this constant may be very strong if p is large. So to deal with large number, and in fact this p large, you can also it can be also penalizing in the bootstrapping process. So it's in general useful to deal with the small p's. So in order to be able to treat large p's also, you use the Chinese remainder theorem, or the RNS process. If you have a p which is large, you just decompose it as a product of co-prime pi, and then you just take the Chinese component of mu on TP1 cross TP2 until TPK. And you encode if every component with small, then the pi is small in TPI. TPI is in general much smaller than p. Then you can do it without any penalizations. You obtain a family of LWEs or ring LWEs, and you can decrypt. You can do the reverse way, and you obtain the decryption and encryption. So this is very, very easy. No problem. And now let's come to the cyclotomic polynomials, general cyclotomic polynomials. So you know what is the definition of a cyclotomic polynomials. I just give the definition here. Is the unique irreducible polynomial with integer coefficient that is a divisor of x to m minus 1, but not a divisor of x to k minus 1 for any k strictly smaller than m. Okay, then phi is classically given by this expression here with complex numbers here. Phi is has an integer coefficient. Its degree is phi of m, where phi is the so-called totient function. And phi is very, the family of cyclotomic polynomial is very known. Their expression is very known. You can find this everywhere. And what is of particular interest for us is the case where m is a prime power, and in this case you have a simple expression of phi m, which is this sum 1 plus x over to the power m over t, etc., until x to the power n. In fact, phi of m. Okay. Okay. Now I just want to show you some algebraic tool that we will use in this analysis, in this construction. So first, the modulo. If you have a polynomial, in a polynomial p of degree m, you can take the modulo phi m very easily, of course. And you have a formula, nothing very special, nothing very hard here. You have a formula of taking the modulo. The modulo, in fact, the modulo is more complex if you have a tensorized or more composite M, which is composite, not just a prime power. But we can do it also by tensorization. It's not a problem. You have a very important mathematical tool is the trace. The trace, what is the trace is defined on the Galois extension K, which I presented before. And what is the trace of P? The complete trace, not the partial trace, but we will have partial traces also. The complete trace is just the sum over all the P of x to the power d. This is, P of x power d, over all d which are prime with m. This can be also written in terms of Galois group. So the Galois group is just the set or the group of automorphism. Tau d is defined here. Tau d of x is equal to x to the power d. This is automorphism. This is the family of automorphism when d is prime to m. It's family of automorphism on K. And you sum, trace is just the sum of on all the automorphism tau d and we sum what? We sum tau d applied to P, which is P of x to the power d, because tau d is an automorphism. Okay? So this is just the usual definition of the trace. And this trace allows us to define a scalar product. The scalar product is defined by scalar product on K. K is also a linear space on Q. You define a linear product like this. You take the trace of P bar of x by Q. This is the scalar product P by Q. And where P bar is just P applied to x minus 1. X minus 1, of course, is the same as x to the power m minus 1, because we are modulo phi m. Okay? So this, in fact, we can show that this is a scalar product without difficulty. And this scalar, we can define also duality. We can define the duality of this space vectorial, the linear space we use. But what will be of great interest for us is the dual basis of a basis. If you have a basis omega I in K, basis of polynomials, not necessarily the canonical basis, another basis, you can define a dual basis, which is defined like this, as usual, omega I star, scalar product with omega j is equal 0 if I is different from j, and is equal 1 if I is equal j. And in the case of, this is very general, but in the case when m is a prime power and when omega I is the classical, canonical, I should say, basis, we have omega I star. We have an expression which is simple here of omega I star in terms of the canonical basis. You are just have here a notation. This notation just means the modulo of I with respect to m over t. Modulo, this is I modulo m over t. Okay, and you have an expression. And you can tensorize, again, this expression if you have a composite number. Okay, now, as I said, you have now from practical point of view, how to deal with this duality and this scalar product. So we defined first, so K, you know what it is. I defined it already several times. R is the ring of integer associated, the ring of integer of K. Here phi m is cyclotomic, so R is the ring of integers. And R, for practice, you can describe it as linear combinations of omega I of x with integer coefficients. Omega I is the canonical basis here. We can define the torus, the polynomial torus. What is the polynomial torus? It's just as usual. It's just the polynomial, this t of x, and we take the quotient by phi m. It is the same as the field K quotiented by R, and it is in practice how we will deal it with, how we will deal with it in practice. It's just the linear combination of omega I where the coefficients are in the torus. And we can also define their dual. The dual of R, this is RV here. The dual of R is just the linear combinations of the omega I of star I defined it before of omega I star with the integer coefficient. And we can show that this is just omega 0 star multiplied by R, where omega 0 star is just the first polynomial in the dual basis omega I star. Okay, and we can also define the dual of the dual of T, of the Z module T, and it is just defined as the linear combination of omega I star with coefficient in the torus. So this will be of interest for us. And in fact, we can, in fact, the ring LWE, if we want to define the ring LWE encryption, we have to go back to what did Regev in 2013, because in fact, we need to do it exactly as he did, because he has proved that this one has some security, has some etc. So we want to go back to what did Regev in 2013. I will be maybe more clear in few seconds, in few minutes. So if you take what is the RW, what we call RW star is an encryption of a message mu star which is in the dual of T, not in T. But if you want to encrypt something which is in T, you just multiply it by omega 0 star, and it becomes in TV, in the dual of T. And then you proceed as follows. So if you take mu star in TV, you just sample a Gaussian E star in TV. How to do this? It's just to sample, to take Gaussian sampling of its coefficient in the dual basis omega I star. Okay, and then you sample uniformly A star in the dual of T in the same way, using the basis, the dual basis, component-wise in the dual basis, and you compute B star as usual is equal S of X, A star plus mu star plus E star, and this is of course now not modulo R as usual, but now it is modulo RV, and the output result is E star, B star, the couple E star, B star. Okay. Now, if you want to make a parallel with the usual, let me say maybe classical ring LWO, as you can find it in the literature, at least in the practical literature, you can multiply just this E star. I made a mistake here. You can just multiply this E star. This is E star here, and this is B star here. Sorry for the mistake. You can multiply E star by omega 0 star minus 1, which is a polynomial, because we are dealing we are working in a field, and you multiply also B star. This is B star here by omega 0 star minus 1. You get. Then you can see that the form of the encryption is the same as the classical ring LW, but with an error which is different, which is we see that the error E star will be multiplied by a polynomial, not just a constant. This is a polynomial omega 0 star minus 1. And in this case, we can see that in the case T equal to, in the power 2 case, this factor here, which was a polynomial, is now just a constant. It's a constant polynomial. And in fact, since in the prime power case, this is not constant, we have to be careful with what we are doing, because, for example, the components of E, of course, they are Gaussian, but they are not the sum amplitude, and they are not simpled in the same way. All the coefficients are not simpled in the same way, and they may be dependent. The sampling of the coefficient in E, not in E star, but in E, they may be dependent and are not sampled by the same, let's say, the same standard deviation for each coefficient. I don't know if I'm clear, but okay. Okay, so the security is not my concern here, because all the LWE and the ring LWO that we use here and use in our work are based on the classical security of LWO and the ring LWO. So we can, in general, what we do is to use the latest estimator designed by Martin Albrecht's team, and it's okay for us. Okay, now let me come to the bootstrapping. Bootstrapping is how to formulate bootstrapping. The goal is how to formulate bootstrapping for general cyclotomic polynomial. What is bootstrapping in general? Bootstrapping is if you have a message mu with some error, if you have an encryption of a message with some error, and if you have a given function f, which is clear, how to compute a new ciphertext encrypting f of mu. with a smaller error, knowing that only you know only the encryption of the key. Of course, you don't know the key. And in fact, the general strategy is to choose a decryption formula. A decryption formula, what I call a decryption formula, is a function theta, which satisfies theta of mu plus some error is equal f of mu, f is given, for all mu in TP, okay? But the error, provided that the error is smaller than something like 1/2 pi or less than this. It depends on the problems, but in general, it's this, okay? This is the bound, okay? This means that if you find such theta, this means that theta, you can replace mu plus A by plus E by B minus S by scalar product of S by E. So the error is over. There is no error in this formula. Okay, and then you have just, it's not easy, but you have to just to encrypt maybe the component of S or something to encrypt S in order to get a homomorphic encryption of this formula. If you get a homomorphic encryption, an efficient homomorphic encryption of this formula, then you succeed to do your bootstrap. But the challenge is this point, actually. This point is really this point. How to do how to perform an efficient theta, how to find an efficient theta. And this is the idea, at least this is the idea by Ducasse and Misiencio in 2016. They were able to find a formula, tricky formula that satisfies this constant. The formula is this one. It's just you have a message mu. You transform it you rescale it by m, because mu is modulo 1. So now m mu is between, let's say that it is an integer. If it is not, you just round it. Okay, m mu is between 0 and m minus 1. So you encode this, you put this in this component, and you see you look for the eth component of v. The eth component of v, where e is just m mu. And in the eth component of v, and we are looking for v, such that the eth component of v is exactly f of mu. Okay, this is the game. And if you succeed to do to construct this v must satisfy, of course, must support some error. So you have some redundancy in this polynomial. You have the coefficient will be repeated in some sense, because you need to kill some error. Okay, this is just to say that the coefficient of v, I of v, is redundant. And if you succeed to have this formulation, then you will succeed to do homomorphically. You will succeed to do bootstrap. But you need, of course, you need to replace this by the phase, and you need to have a reduced complexity. Of course, this is the game. Eh? Okay, before maybe just explaining this fact, I just say that this formulation has a drawback in some sense because of the so-called negative cyclicity condition. If you replace mu by mu plus half here in this equation, then you get the minus sign, because x to the power n is equal minus 1. I am, of course, talking about the case of the power 2 case. So you have this, the function must satisfy this condition, f of mu plus 1/2 plus f of mu equal 0 for all mu. So this can be removed easily if p equal to, if you have binary messages. But if p is bigger than 3, then you have to do some, you have to do some complicated things, but you are penalized in some sense on the error, or you have to pay something. You cannot, there is no free lunch, you have to pay something. Okay, now I just here just say that of course the x power minus m mu is very useful because it is a product. It is a product. It can be because the component is linear in S. You can just write this as a product of something which depends only on S1, something which depends only on S2, and something which depends only on Sn. And this is important to break, in some sense, to break the complexity this homomorphic evaluation. Okay, so let me just, now if you have a more general cyclotomic polynomial, how to do this bootstrapping. In fact, how to do this, how to transform this Dukas-Missions-Yu bootstrapping function. In fact, the natural thing is to say that now I think I take this theta equal to omega with an index here, which is m by mu. It's the same trick, but with the scalar product with v, and we are looking for v that satisfies the relation theta of mu plus e is equal f of mu. And this scalar product is the formula of the scalar product, and this suggests that v will live in TV, the dual of t, not t. And if you take this v, if you look for this v there, we end by this formula. I will not give you the techniques. We end by a very simple formula for v. V is just, depending on the function f you are targeting, of course, you have this simple formula, okay? Okay, and so it's very simple to find v. Now, what about the negacyclicity condition? So the negacyclicity condition is I don't know if I can explain. Yeah, maybe I don't know if I don't have enough time, but the negacyclicity condition is just to write where does it come from? In fact, if you define omega I, this is omega I is the encoding of the message here. I is the km over p, or its rounding. If you define f of I is equal omega I by v, you see that this system is not a square system, if I could say. I mean, the number, the v has n coefficient, because v is modulo phi m. But the I here, the index I here is between 0 and m minus 1. So you need to solve this linear system, you need m minus n compatibility conditions. This is the so-called negacyclicity condition for the power 2 case. But for the general case, you have many compatibility. You have m minus n compatibility conditions. You have m over t compatibility conditions. And we can write them here in terms of this capital F. But and you can write them also in terms of the targeted small f. And you have here m over t relations, negacyclicity relation. This is equivalent. If you have this negacyclicity relation, then you can solve, you can find your v. And in fact, now the difference between the case of t equal to and the case of general prime power cyclotomic polynomial is the following. In the case t equal t2, you have p over 2 negacyclicity condition. This means that you have the half of your message space, which is equal to the opposite of the other half. And here we can show that this is not the case. For example, if you choose the p, which is the number of messages equal to t, then you have only one negacyclicity, one compatibility, I should say, relation, which is this one. And this is already one is very good because it has nothing to do with it's not really a problem, and you can remove it easily by just subtracting. If f does not satisfy this relation in blue, then you just define f tilde like f mu minus the sum, this sum here, divided by p, and this f tilde will satisfy the negacyclicity, the compatibility condition, and at the end we deal with this f tilde, and at the end you add just s over p. It's okay. Okay. Now, as you know, in the bootstrapping in general, in the bootstrapping, at least in the bootstrapping process, you need an extraction somewhere because you have a trace, or we have a coefficient 0 or something like this. You have to extract because you are dealing with a ring LWU, and you have to pass to extract some LWU encryption. So I just show you very simple way using this context of duality how to extract in any basis, how to extract LWE of the coefficient. Now imagine, so here I will not treat the two cases because the two cases are dual one of each other. I will just take the case of mu, where mu is expressed, is in T, where it's expressed with the canonical basis omega I, okay? And I want, you know, a ring LWU of mu, and I want an LWU of mu, okay? Of mu I, sorry, mu I. Or any linear combination, in fact, of mu I. Now, what you did is simply, we multiply this encryption relation by omega I star. So you obtain omega I star by B, scalar product. You take the scalar product, what we defined before with the traces. And you get, by definition of the duality, you get here mu I plus mu omega I star by E. Okay? And now you just decompose the key S in any basis of your choice. We call it B, for example, and you get an LWE equation, an LWE encryption equation like this, which means that the mu I has this, the LW of mu I is the following, is composed by A tilde and B tilde. B tilde is this one, omega I star by B, which we can compute by hand. There is nothing to do, just to compute it by hand and to implement it. And here also you can compute this scalar product by hand because E is in clear, and you compute and you just implement it. And in fact, this can be generalized to blind extractions, but I will not talk about this here because it is a patent which is patent pending with CNRS, INRI, and Ravel. Okay, let me now just talk about if you want to now to extract a ring LWU of mu I from a ring LW of mu, not LW of mu I, ring LW of mu, then you need something else, because I just show you briefly how to do. You have an RLWE of mu here. What you do is just to multiply it by omega I star bar and call this mu star, okay? And you know that A star and B star are the encryptions, if you want, of mu star with error U star RLW encryptions. So you can write the equation satisfied by A star, B star, and mu, and you write it. Okay. Yes. Yeah. Then once you have this, sorry, I'm just confusing here. Well, you take mu star is equal omega I star by mu bar. Here you have the bar. Then what you have just to compute is the trace of mu star, because the trace of mu star is mu I. You have to compute homomorphically the trace of mu star. How to compute homomorphically the trace of mu star? You do these things. This is something which you can find in other forms in the literature. You take the equation, you apply the equation of encryption to x to the power d, when you have this equation. But you cannot sum over d because s depends on d. So you perform a key switching from s of x to power d to s of x in order to make this term d independent. So you obtain a new equation, and then you sum over d. Then you have your RWE of the trace, and you have your RWE of mu I. Okay, this is okay. You can also do this. It's more involved. You do this by in a blind extraction. So you don't know what you are extracting in some sense. But I cannot maybe talk about this in this talk. Let me just to say that the evaluation of the trace can be expensive if you don't do anything. But since you have to compute this trace in a much more rapid way. There is a way, in fact, to compute this trace very rapidly. It's to factorize the trace. We have to factorize the trace. In order to factorize the trace, because yeah, it's very expensive. As I said before, it costs n square log f of n multiplication. What you do is just to use Galois theory to decompose the trace, because in fact between Q and K you can insert many extensions to compute the trace of key over Q. You compute it first over some extension which is between the two, and another extension between the two, etc. And you can do like this and reduce the complexity. So what is Galois theory? Is probably already know what Galois theory says. It says that for any subgroup H of the Galois group, the Galois group of the extension K over Q, there exists a unique extension, intermediate extension KD, such that the Galois group of the extension KD over Q is exactly H, and the order of H is exactly the dimension of the linear space KD over Q. Okay, just to say that if you have a sequence of a divisor of divisors of n like this, D1, D2, DR, you can insert several extensions between Q and K like this. And instead of computing directly the trace of K over Q, you just say that the trace is the composition of the first trace here, second trace here, etc. And you see that the complexity now is because each trace has for example, this trace, the last trace has dr element, dr automorphism to do. The other one is dr minus 1, etc. Because the dimension of KD1, for example, D2 over KD1 is D2. Okay, so the cost of this trace is just D1 over minus 1 because we don't take account the identity. D1 minus 1 plus D2 minus 2, etc., which is much less, much smaller than the original complexity. And for example, if you take this sequence of divisor of n is equal T minus 1, T multiplied times T alpha minus 1, you take this sequence of divisor, you see that we pass from n automorphism to log n automorphism. So it is a considerable gain. Okay, now one may ask, what is the function, or what is the action of these traces? If you take just a trace of an extension kg plus 1 over an extension kg, an intermediate trace, which I call here trace J. Okay, if you take this, what is the action? I mean, the Galois theorem is an abstract form. We need some concrete applications. So in fact, this trace, if in our case, we can see in the case of prime power cyclotomic field, you can see that this trace G serves to eliminate all, in a polynomial, serves to eliminate all the powers which are multiples of m over t to the power g plus 1, but not multiples of m over t power g. But this is very useful when you want to do, for example, packing, and you want to do fast packing, because you manage to kill some terms. I will show you, maybe if you have just a few minutes, show you how to do this. Trace zero works similarly, but just you have t minus 1 instead of t, so you have just to be careful with this. Okay. So okay, now just to, of course I will not explain how fast packing works, but I just remember that the usual packing, or the natural packing, if you want, it works very simple. What is packing is just to get a ring LW encryption of of polynomial mu in some basis, whatever the basis can be, some basis, sum of mu I bi from LW encryption of the coefficient mu I. This is the general principle of packing. And in fact, what the classical or natural way to do it, if you write just the equation satisfied by mu I and its encryption is this one, then just you multiply by the basis bi in which you want to pack, and you have this formula. Now you want to pass from LWE, you want to pass from LWE encryption to RWE encryption, then you have to encrypt each component SJ in ring LWU encryptions. Okay, so you encrypt the component SJ in RLWU, and then you obtain the encryption of the packet, the ring encryption of mu of X, ring LW. Okay, so you see that but the problem is this packet in general is very expensive. As I said, it costs almost the same thing as a bootstrap. Okay, so for example, if for D relatively small, the complexity of D n square, and if D is large, the complexity of n square log n, approximatively. Yeah. Okay, now if you want to just transform an LWE encryption to a ring LWE encryption. This has been done by Chen, Kim, and Song in the Power 2 case, and we tried to apply their method and to extend their method for general cyclotomic case. And in fact, it works, but you have to adapt with dual basis. This is another interest of the dual basis. We succeed to adapt their idea. I mean, and in fact, it works because if you have some mu0, an LWE, some mu0 which is encrypted in LWE system, so it satisfies this equation, then you just form A tilde like this, but S tilde should be formed in a suited way. You have to choose the form, and this is the form we should have. And in fact, when doing this, you form mu tilde, we define mu tilde like as being B minus S tilde A tilde. And now we have to clean this mu because only the coefficient 0 is interested in this. And to clean it, you take the trace. After multiplying, you take the scalar product by omega 0 star, and you apply this algorithm of evaluating the trace homomorphically, as I explained before. And you can see that this one is not as expensive. It's much less expensive than the other one. Okay, so I think I conclude my talk by saying that we are extending this work to the composite case, and it is to be submitted soon. So I thank you very much for your attention.